After this, only 3 lectures left, 3 videos. That's it. Hello and welcome back to Calculus 2, section 9.4, working with Taylor series. So it's time to wrap up. It's time to take limits, derivatives, and integrals to see what the Taylor series are good for. Why do we bother with stuff? Because why would you change a function into something else, right? And the only sentence of me teaching this lecture is do calc of Taylor series termwise. Done. So that's the lecture. So now what does that mean? That means that if you have a power series, let's say you have a power series for sine x. We saw it. It's x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot 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 forever. Do calculus of Taylor series termwise. That means if I'm either differentiating or integrating, I will consider each term separately and I will do whatever needs to be done on each term separately. And that's all it is. You already seen me take the derivative in respect to x of sine x, and we obtain the cosine x equation. So derivative of x is 1, and then minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot dot dot. It is a power series. How about to test the integral of e to the x dx? I told you that the integral of e to the x is e to the x because the derivative was e to the x, right? But really, is it that?
Yes.
Well, yes, right? Because you are going to write this e to the x as 1 plus x squared over 2, right? Plus x cubed over 3 factorial plus dot 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 dx. And when you integrate, what do you get? You get integral of 1 is x plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus dot dot dot. And you know what? There's a plus c at the end. Now some students laugh at plus c at the end, but without that plus c at the end we don't get to prove anything because that's where the 1 is hiding. Do you see this 1 over here? Do you see that there is no 1 over there? There's the 1 that goes over there and becomes that plus 1. So that plus c is going to give us the 1 that we need. So I'm going to link that using the red color. There we go. And then we have plus x squared over 2 plus x cubed over. Now, how much did I take outside of that c? I only took 1. So how much did it left? Well, it's still c left. So I have e to the x plus c as the answer. So I'm borrowing 1 from that c, and then the rest of c stays there.
Can I borrow like 2 or something?
Yes, you can take any amount of the constant you want. Any amount is okay that needs to be added or subtracted to the entire section. But these basic integrals and basic derivatives and basic limits are not why we are here tonight in such a great numbers. We are here to see the function composition at work. We are here to integrate something that we can't integrate other way, like e to the x squared. You see, when you have integral of e to the x squared dx, you need that x in front so you can do u sub, right? Now, when you're looking at this, you can just cry, right? Because there's nothing we can do to integrate this so far. There's some other things that you can do later on, but right now. So what do?
Do the 1 plus by x plus by x squared over 2.
Well, that's for e. And that's correct. That's where you start.
You square it. You want to square it.
So what we're going to do is we're going to build e to the x squared using composition. You start from claiming that e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus dot dot dot. And what you do is now you replace each x with x squared and you perform the algebra. So now e to the x squared is equal to 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 3 factorial plus x to the 8 over 4 factorial plus. You see what happened? We replaced every x with x squared and we are getting the power series for e to the x squared. And now, haha, our integral, easy. I am integrating polynomial. And this 3 factorial is 6. The 4 factorial is 24. This is why these power series are so powerful. They take functions, they transform them into polynomials, and then your derivatives and integrals are joke. What do you have to be careful about? You have to be careful about precision. Do you keep one term? Definitely not. So you have to develop through the, you develop that sense when you start working, whether you have to keep 3 or 4 or 5 terms, because that will be linked to the precision of your calculations, which is very important. You also have to be very careful where you expand your functions. If you go and you say that you want to compute the integral from from 10 to 12 of e to the x squared dx, and you used what you have above, well, I'm sorry, it's not going to work. It's not going to work because this expansion here is centered where? At 0. And this integral is centered where? At 11, right? Because that's midway between 10 and 12. You can also center it at 10 if you want to. So you get the idea. You have to center your expansion along the important point. We don't usually do this for derivatives because you can always take derivative. You can differentiate anything. We also have a logarithmic and implicit differentiation. We have product rule, chain rule, quotient rule. We have a whole spiel. There is no method that you learn in Calc2 to integrate e to the x squared. And there's a whole bunch of functions that cannot be integrated at all. But they can all be transformed into a power series, which is a polynomial, and then you decide whether you keep 3 or 8 terms. And you have to make sure that you are centering those around, if you have a definite integral, around the region that is in question. And that's the lecture. I know, what can I say, 15 minutes, if so. Yes? Oh, yeah.
Basically, how, so you can't be able to do this one. I mean, like, when I do it, I got to be.
Well, we have to expand this. So each one of these x's would be x minus 10.
X minus 10.
Or x minus 11.
X minus 11.
Because 11 is halfway between. So you have to expand close to the interval. You remember how when we had the sine expansion, the further away you go down the line,
it's like
the lines were diverging from each other? This is not going to converge on this interval that far away.
Are you going to be showing some examples or not?
Where's the example? What do you mean?
No, I mean like a equation like e to x plus by 1, for instance. You can like do du equals du, and then you said e to u.
By ex plus 1, you don't need to use this.
Okay.
E to the x plus 1, you can use basic u sub. This is going to be used for the functions that you cannot integrate. So anything that you can come up with that you can do with a different method, that's the method you use.
What with my math lab, how would they want it to be?
To be honest with you, I have no clue until I see it. Because, as I said, you have to expand the function. If you have a definite... So this was an indefinite integral, right? Nothing on these, nothing on the limits. So we put some terms and we're done. This is applied problem. So this one, you are expanding, right, 10 to 12. You are expanding this 1 plus x minus 10 squared plus x minus 10 to the 4th over 2 plus x minus 10 to the 6th over 6, and I got tired. Dx. So you have to expand around points of interest. You can't go and say far away, because if you remember the graphs, right, for sine, which did this, right, your x did that, the other one did this, right, and then the next one did that. They all, if you're here, they're really divergent, right? They don't give you the same answer. The answer you get from the integration will be garbage.
May I ask, what interval would I basically know what to use? I know you said x minus 10. Would I use the lowest interval?
Yeah, that's what I used.
Okay.
Because this 10 to 12, this 10 to 12 are a and b on the x-axis, right?
Okay.
So your function looks like this, something like that on 10 to 12. So if you do expansion around 0, the function will look something different there, right? So you are centering your expansion at 10, and then the function might look, I don't know, something like that, but it's close enough. Because these are approximations, these are not exact values. How do you get exact? You do the actual integral, infinitely many terms. So that's what we have. That's what we have for this section. You will take derivatives, you will take integrals, you will take limits, but the nasty function you have will be transformed through power series, and then you will see. So you can think about your own examples, guys. Stuff that you can't integrate, right? You say like integral of sine x cubed dx. You can't integrate this because there is no x squared in front, right? It can be integration by parts. Nothing works. Nothing that you learned works here. So I'm going to challenge you to solve this problem. You will solve it this way. You first build up the function from power series in the same fashion what I did in blue. You build up the function, and then whatever power series you get, you stuff that into integral, and then you're integrating polynomial. Easy stuff. Then you add another level of complexity, which is limits. So now you have to do the stuff in blue, and you need to expand around whatever the limits say. So that's another layer of complexity. The integration, derivatives, limits, everything will be easy to do because you're always doing that on the polynomial. And you do it term-wise. So the tricky part is the blue part. To recognize that once you write the power series for this, right? And then don't stop there. You can go and integrate anything then, right? Figure it. Yeah, so you figure it out, right? You figure things out, and you start writing things to try to figure out one way or another way, right? You build up your own functions. And when you come up with a crazy integral, ask yourself, because you made it up, can I do the U sub? Can I do the trig sub? Can I actually do any of the conventional techniques that we learned? Because this is going to be an option for you. And then once you become masters of this, there's a 400 level course math that does only this stuff. And then there are 2 courses called asymptotic methods on the graduate level, 700 level, with more of this stuff. When you plug a series into a series. So you have, this is not you plug a function into a series. You have a series that have infinitely many terms, and within each of those infinitely many terms, you have another series with infinitely many terms, and they get nested. And you can dig that way as deep as you want. It's a series of a series of, you can nest that. It's awesome. So a lot of stuff ahead of you. You can build this up. Welcome to 1800s. Yeah, I know. Welcome to 1800s. You should be looking towards your Calculus 3 and your differential equations, which will keep you in 1800s. Both of those courses, yes. Both of those courses will keep you in 1800s. And then you will start peeking out of 1800s with certain concepts from linear algebra. Most of it is 1800 still, but some concepts of linear algebra are in 1900s. So now we'll start talking about, you know, First and Second World War era. And yeah.
If anybody ever makes a time machine, totally going in it and just ripping everything from calculus and like jumping to the 1700s, 1600s.
What do you mean?
Everything will just be Walton everything. They'll have my name all over it. I'll just do the Walton series. Yeah, exactly. So I'll jump back here and be like, what's up, Professor Nick?
Professor, I have a hypothetical question.
No.
So let me just end the stream first. Yeah. Say, all right, so we say bye to the, we want to preserve the viewer base.